Good morning and good afternoon, everyone. Thanks for coming back to this wonderful event. I'd just like to remind people that we have a poster session tonight after the afternoon talks. And the way that it will work is that you can check out the video recordings, the pre-recordings for these posters at any time. And I encourage you to do that throughout the day. Before the poster session, as a matter of fact. You can find in the website a list of the posters in the posters tab. It's a numbered list, so there are 7 posters. There are not too many, so you can check them all. And then if you're interested, you can jump in any of the breakout rooms, which will be numbered according to the recordings in the website. And so there you can ask questions and expand on the topics if they are of your interest. And also I would like to remind you that the videos of the talks are being posted in the videos and files tab. So thanks, Thiago, for that. And so if you want to check them out again or make additional notes and open up discussions actually in the Slack channel if you wish, that is also available. Thanks a lot, and I guess I'll leave it to Steban to chair the session. Thanks.
Okay, so let us start with this session. Afternoon, I think almost everywhere. It's a pleasure we have Camila Machado today that well, she's originally from São Paulo. She did the PhD there and is now in DESY. After having done a career through CERN and through Mainz. She will be talking about on-shell amplitudes for effective field theories. Camila?
Can you see my slides?
Yes.
Okay, very good. So thank you very much for the invitation. It's a pleasure to be here. Actually, I think the SILAFAE was the first conference that I attended in 2012 when I was in São Paulo. And I think Nayara was there with me. So it's like nice that almost 10 years later, we are here now, but this time as the speakers. So I'm going to talk about amplitudes for EFT. So I'm assuming that not everybody's familiar with the topic. So it's going to be kind of a long introduction. And then at some point, I'm going to talk about an application that was this paper that I did in collaboration with Adam Polkowski and his PhD student, Julie Isabella, that is applying these on-shell methods to construct a higher spin dark matter model. So when talking about amplitudes, the first thing that we think about is kind of the Gluon scattering. And kind of the 2-2-2 amplitude, everybody at some point in life did by hand, and it's not many diagrams. You can, compute this. But for 5, 6, or more gluons, it's very fast to become something very complicated with like many, many diagrams. So it was quite a thing when in the 80s was this paper by Park and Taylor with a formula for the n-gluon scattering amplitude. And the thing is that they realized that there is actually a clever way to organize the calculation, writing everything in terms of a list amplitudes. In this way, it gets much more clear the structure behind the amplitudes, and they could make a conjecture for this formula of the any-point amplitude. Now, if you look to the citation recorded record for this paper, there's kind of this phase transition. And around 2003 was this paper by Witten. And the thing is that it became clear that this structure that they're seeing in the n-gluon scattering was not particular from, Yang-Mills, but actually that scattering amplitudes have a very rich hidden mathematical structure that is far from obvious when you're just staring the Lagrangian. So I would say that this was kind of the start of this amplitude program. And the idea here is kind of to avoid Lagrangians and all the redundancy and complications that comes with it. And now like really work and trying to understand better the structure of the amplitudes, which get you closer to the observables. So one of the motivations was also that was necessary to compute amplitudes with many loops and many lags to have a better understanding of the collider background. And in this case, it was also along the way was they realized that there was many insights that were found when looking to the amplitudes. Now, what I have been doing in the past years is to apply kind of the same logic, but now thinking about beyond standard model. And now I'm not focusing on the background, but in the collider predictions. And indeed, we are in a situation where we are not clear where is the new physics. So we need more precision, we need more loops and lags also when we talk in the context of BSM. And also, like any new insights about BSMs are actually welcome. So looking at things through this new perspective can actually be very useful. Now, talking about BSM, one of the most useful frameworks is talking about effective field theories. And the idea here is that your the standard model, for example, is your low energy theory. You have a UV theory that you don't know what can be. But you still can study the deviations of the standard model through the so-called standard model EFT. You can also include some extra degrees of freedom in your low energy theory, for example, some dark matter particle, and then study what people call in general this dark matter effective field theories. Now, from the point of view of Lagrangians, what you need to build the EFT are Wilson coefficients that are these parameters that encode information about this UV theory that you don't know. You have your lambda, that is the cutoff of the theory. And you have your operators that are made of the fields of your low energy theory as well. Now, the Onsha way, as I was telling you, is we are not going to talk about Lagrangians anymore. So what we do instead, we are going to already start with a general ansatz for the amplitude. We are going to apply some consistent conditions. And this will give us what I'm calling the physical amplitude, some that would correspond to a theory that can or not come from a well-known Lagrangian. So to give a concrete example, here I have a scalar EFT. So for example, you're going to start building operators with like 4 scalars. You can include as many derivatives you want. So in this case, you still have a non-trivial step that is apply equations of motions, integration by parts, field redefinitions to see what are your independent operators or what is your basis of operators. So in this case that I wrote, that is indeed just one independent operator that you get in the end. Now, when we talk about the amplitudes, with 4 fields, we know that we just have the Mandelstam variables STU. So your amplitude is a polynomial in these variables. Now we are going to apply momentum conservation and your own shell conditions. In this case, that the particles are massless, just p squared equals 0. And you find out that at least at this order, there's just one polynomial that you can write that satisfy all these consistent conditions. That this is this s squared t squared plus u squared. And it is in fact, it's in one correspondence with the operator that you would write in the Lagrangian. So this is one side, one application that doing the Onsha way, it's easier. So building an operator basis and studying the EFT landscape. So I just want to kind of list the things that haven't been worked out in the context of EFTs in the past years. So one thing is this construction of operators basis, and this was also discussed in the context of the standard model EFT. There was also a lot of development to compute amplitudes with many external legs using the so-called recursion relations that make it very efficient to build higher point amplitudes. There is also some exploration of EFT properties. So for example, elastic selection rules and soft theorems. Also, the calculation of loops, it's much more efficient in this way, and this is very helpful to compute a normal dimension matrix, and it studied its properties. So this is also been done in the context of the standard model EFT. Now, other thing that is very helpful to work with amplitudes is when you have to do with gravitons, and here there's something very, very interesting that's called a double copy that relates the amplitudes of the Yang-Mills series with the amplitudes of gravity. And this type of structure can also exist for some special EFTs. And another point that these on-shell methods can be very helpful, it's like dealing with higher spin particles. In this case, it's just because you avoid building a Lagrangian. Building a Lagrangian for a particle of spin, I don't know, 3, 4, it's like a nightmare. So in this case, we are, this is the example that I'm gonna tell later, where we could build a dark matter model for a dark matter of any spin without writing any Lagrange. And just to mention, a lot of this development is for massless particles, but since this paper of Arkan Hamed, Huang and Huang in 2017, there was also a very convenient formalism to describe massive particles. And a lot of these things have been developed also in the context of massive theories. So this was kind of a long introduction, and now I'm going to talk a bit of the Spinor basics and writing amplitudes in the massless and massive cases, and then I'm going to move to the dark matter EFT. I want to talk about two scenarios. The first one that we described, just a gravity mediated scenario that would be the nightmare for any experimentalist. And also the case of a Higgs mediated scenario where you can have more phenomenological signatures. Okay, so some Spinor basics. So the first question is why we should use spinors. And the answer is that it gets more transparent to see how the Lorentz symmetry can constrain the functional form of the amplitudes. So now I can write my momenta p mu contracted with the sigma mu, and this can be described in terms of multiplying two spinors, lambda and lambda tilde. And they are going to satisfy a very simple transformation under the Little group, which is the transformation that leaves the on-shell momentum invariant. The spinor lambda is associated with particles that we label with LST minus and the lambda tilde with LST plus. And the whole amplitude will, in this case, that the particles are massless, the Little group is just U1. So you just have a phase that is going to go in this form with -2 LST of each amplitude of each particle of the amplitude. So just to not be something very mysterious, if I write, for example, my momenta in this parametrization in terms of angles θ and phi, the spinors here are just lambda, lambda tilde, they just have this simple form. One thing that is very usual in the literature is to use this bracket notation, where you call this spinor lambda as an angle bracket with the momentum p, and the lambda tilde with the square brackets of the momenta p. What is very useful that we're going to build the amplitudes are these Lorentz contractions with the angle and square brackets. So we are just contracting with the epsilon tensor. And this is just easier to remember that when you multiply angle and square brackets with the same numbers like this, you just get the Mendelssohn variables STU in the case of 4 particles. So we can all just see some examples. If I write a 3-point amplitude, let's say with 1, 2 square brackets, I can right away read what are the LST of this particle. So in this case, do the transformation with the Little group that again goes with this -2 HI. So the particles 1 and 2 here have LST plus 1/2. And since the particle 3 is not appearing, it's because it's a scalar, so has no transformation with the Little group. If I have a 4-point amplitude, then I write now 1, 2 square, 3, 4 square. Now I can read that my particles 1 and 2 have a list +1, and my particles 3 and 4 have a list -1, and so forth, so on. So it makes much easier to see how the form of the amplitudes are constrained by the little group. So, and this is so powerful that indeed, when you use just little group locality, the 3-point amplitudes are completely fixed. And here, just one remark that since I'm talking about massless particles, the 3-point amplitude vanishes. So we just use complex momentum. And this is useful because we can build 4-point amplitudes using 3-point amplitudes and higher point amplitudes using 4-point amplitudes. So this is useful to define the 3-point amplitudes in this case. So this is completely fixed. So just depend on the list of the particles, and you have this kind of master formula here. So in the case that you have, let's say, 3 vectors interacting in this 3-point vertex, you normally would write all the polarization together. So you have this expression in terms of polarization and momentum. But now, since we are separating in terms of the list amplitudes, we can, in this case, write a --++ or a ++- amplitude. And just using these formulas, you get these 3-point amplitudes here. Now, there is something funny about these vector amplitudes. They're indeed, if you look, inconsistent with Bose symmetry, because exchange this 1, 2 here is unsymmetric. It's going to pick up a sign. So in fact, these amplitudes are not consistent with Bose symmetry, and you are just forced to multiply this by an unsymmetric tensor. So at this point, I don't know what it is. It's just an antisymmetric tensor, but we can keep going. Now it's consistent and build what is our 4-point amplitude. So as I said, we can now build the 4-point using the 3-point amplitudes. And here, if you try to get the correct poles in the T and U channel, you find out that your amplitude has this form. So you can write it in terms of with these 2 terms, one with ST poles and one with SU. Now, if you take this amplitude and check if it gives you all the correct pole in the S channel, what you find out is that the residue in the S channel has a T and a U pole. But if you calculate directly, you see that the residue in the S channel actually just have a U pole. So there is some inconsistency when you use this formula and this formula. Or saying another way, it seems that doesn't work out to get the ST and U poles correctly with the same, writing the same expression for the amplitude. And the way around that you have is that this is just going to work out if there is a relation between these antisymmetric tensors. And the relation that they have to satisfy in order to get the correct poles is exactly the Jacobi identity. So here we see that we just recover Young mu's from unitarity localities and Lorentz symmetry. I don't need to, in any way, to refer to gauge invariance here. And I recover that this has to be a Lie algebra. Now, for massive amplitudes, as I said, the little group is the U1, and we are labeling the particles with the helicities. Now, the momentum is decomposed in terms of these 2 spinors. And you can, for example, write the polarization vectors also in terms of the spinors in this way. Now, in the massive case, it's kind of the same logic, just a bit more complicated, because now the little group is actually SU2, and you're labeling the particles with the spin. And now your momenta, you need actually not 2 spinors, but you need 4 spinors. So this label IJ here is running with the SU2 little group index. And in fact, 2s symmetrized spinors can describe a spin S particle. So here you can write the polarization vector for a massive particles. And what is powerful here is that this object contains, for example, if you're talking about a vector, it contains the longitudinal and the transverse polarization. You don't need to kind of choose a reference, some certain direction and decompose your polarization in this direction. One convenient notation that was also introduced in this paper is called bold notation. And the idea is that instead of writing these SU2 indices and write the symmetrization, you can just write a bold number. So bold means massive, unbold means massless. What this formalism make it also very easy is to connect the RI and UV amplitudes through this high energy limit. And here I'm also writing in terms of this parametrization with the angles theta and phi. What are these massive now spinors? Now they're like vectors, they have more components. And now we can, for example, take the high energy limit, take the expansion over m over e, and look, for example, what is this object 1, 2 massive in the high energy limit. What you see is that you have this term 1, 2 unbold, which means that it's the massless one, plus things that are correct with powers of m over e. So this means that there is a relation between this, just take whatever you have for your massive amplitude, unbold the spinors, and then you get the leading term of the amplitude in the high energy limit. Okay, so let me give you a few more examples of massless and massive amplitudes that I think are going to be useful for what I'm going to discuss next. So what I'm going to just make a remark is that the any point amplitudes have mass dimension 4 minus n. So a 3 point in 4 dimensions. So the 3 point amplitude has mass dimension 1, and the 4 point has mass dimension 0, so forth, so on. So here, if I want to write a massless amplitude with scalar and 2 fermions with LST plus 1/2, Nero group tell me that I have to write a 1, 2 square brackets like this. And since the mass dimension is 1, I know that the coupling that comes in front has to be dimensionless. Now, if I write an amplitude with 3 vectors plus 1 plus 1 plus 1, now Euro group requires this structure, 1, 2, 2, 3, 3, 1, for example. And now this has the wrong mass dimension. So I'm forced to divide this by like some scale, mass scale square. And in fact, this is amplitude corresponds exactly to an operator of the type f min u cube that you would add in the Lagrangian. So this is how you can very easily just look into the amplitudes already describe your higher dimensional operators in the EFT. So in the case of the massive one, so for example, if I have massive scalar and massive vectors, you have more terms that you can write. And now you can, in principle, put a mass scale lambda or a mass. And the way to decide what you should do is to look to the high energy limit. And you can see that, for example, this first term comes from the longitudinal modes. So it has to come with 1 over m. And these other terms comes with the transversal modes of the vectors. So this is why they come with the lambda. So this is how you can use easily this connection between this bold and unbold to get more information about the amplitudes that you're writing. So I hope it was clear how we do the EFT the on-shell way. So what we use is on-shell data. So we're gonna just impose the locality, unitarity, and Lorentz symmetry. We are talking about particles and we're talking about masses. So we're not talking about fields and Lagrangians and these other things. So you can add extra IR constraints. So for example, there is a soft limit, or they call it under 0, that in this case, that you want to build a theory with Goldstone bosons, and this has been done also with the on-shell methods for the nonlinear sigma model. Okay, so I think now we have everything that we need, and we can try to apply this in a concrete example. So the model that I want to build here for the dark matter is where you consider that you have a thermal bath with a maximum temperature T that I'm considering that's bigger than the Latteric. In this way, I can consider that standard model is effectively massless. It's not necessary, just make the things a bit easier. I have very weak interactions with a particle a dark matter particle of spin S. And just remember that there is some no-go theorems for elementary higher spin particles, just in the case that they are massless. If they are massive, there is no problem. And here, I'm considering the instantaneous reheating approximation, where this Tmax is approximately the T heating, and the production via the freezing mechanism, where these particles in the thermal bath can annihilate into the dark matter, but not the inverse process, because the interactions are very weak. So if I want to study the phenomenology of this model, and here notice that I'm letting spin S dark matter, so it can be any spin. What we need to do, if you consider, for example, this gravity mediated scenario, is compute these scattering amplitudes. So here we have the standard model going to a graviton, and graviton going to the spin S dark matter, and I'm considering just a Z2 symmetry that forbids this dark matter to decay. Now, the usual way would be like we have now to build a Lagrangian for whatever spin S we are interested in, go to the Feynman diagrams, then go to the amplitudes, and then go to the observables, and then do our Phenom. Just the Lagrangian step, it's very difficult for higher spin, as I mentioned before. So what we can do here is really take the shortcut and already start describing our scattering amplitudes. So again, we are going to use the basic rules of unitarity, locality, and Lorentz, and build the 3-point amplitudes, and build, if we wish higher orders in the EFT, we can build also the 4-point contact terms that don't have any pole. So in this case, the 3-point amplitude that we need is the spin S dark matter with a graviton. And there is just this very compact formula that you can write for this interaction. And here, again, you can let the general for spin S, just this bold spinors goes with the power 2s. This A is just carrying the little group of the massless particle here, that is the graviton. Now you also need the 3-point amplitudes corresponding to the standard model coupling with the graviton. So here again, we can write for spin 0, spin 1/2 or 1. And you have also this very compact formula written in terms of the spinors in this way. The next thing is that you can also add these contact terms, which are very easy to build just using this zero group requirements. And again, this is in the case that you have a scalar, Fermat, or a vector, and all these contact terms are written for a general spin S. So now what you need is to kind of glue the 3-point amplitude. So just multiply them and put the pole in the S channel. And if you wish, add the higher terms in the FT that are coming with this contact term. So I'm showing here the formula for the vector, and I think it's quite remarkable that you get like such a small formula, like 2 lines for a general spin S particle. And also what is nice to get at this formula is that it's very easy to see the energy scaling. So we see that this amplitude scale as e to 2s plus 1, and any contact term that you add scale as e to 2s plus 2. And having this estimative is very nice because you can do what every physicist love and work with like dimensional analysis. So we can work the phenomenology and really understand everything once we have this kind of insight of how the amplitude scale. So you have to solve.
You have 5 minutes. Yeah.
Oh, okay, thanks. So you want to solve this evolutional equation. And here, when you compute the freezing rate, there is where it enters your amplitude square. If you take just these estimatives, you can also see what have to be your maximum temperature to match the dark matter abundance. So you see how this scales with the spin for a T much bigger than the mass of the dark matter. And if it's much smaller, you actually have a Boltzmann suppression. So the dependence with the spin drops. Okay, so this is what we get in the case. I'm plotting here for the spin 2 and no contact term. Here is this temperature to match the dark matter abundance and the mass of the dark matter. So again, this is the experimentalist nightmare scenario, because the dark matter can be like basic any mass and it's very difficult to find it. But what we want to show is like this black line, this dotted line is what is the estimative that we get just with the dimensional analysis, and the black line that's on top is what you get with doing everything numerically, and this deviation here is just this Boltzmann suppression. We plot also here this orange area is the EFT validity, so everything that's here you don't trust your EFT calculation. The green area here is just our approximation of the standard model massless. So in principle, you could correct the calculation, putting mass for the standard model particles and also access this area. And this red band here is just some constraint from small structure formation. So we also in the paper plot what happened when you have higher spin like 5/2 or 3. So for much higher spins, the dependence kind of drops because you're in this regime where you're below this T max, and you are kind of just allowed to be in this part where you have the Boltzmann suppression. We also did the analysis when you have a contact term. So here you have this kind of large values of these Wilson coefficients just because we are normalized with m Planck square. And then you have these lines that correspond to different heating temperatures. So in this case, when you add a contact term, you saw that the energy dependence is stronger, which means that now your temperature can be a bit lower than in the previous scenario. So to this kind of a toy example, and to make the things a bit more fun, we also work out the case where you have a Higgs mediated scenario, and you can, I mean, now you just have more diagrams, but the idea of how you build the amplitudes is pretty much the same. So now you can even include a dark matter self-interaction, so you have an extra diagram like this. And in this case, you're allowed to have this part production, but also a single production channels of dark matter. So here I'm just listing again what are the 3-point amplitudes that you need to make the calculation. So here you have this Wilson coefficient that is also kind of this Z2 breaking parameter that's order n Planck over lambda. And you can also write what is this self-interaction, although this diagram is always kind of subleading. And this, again, you have this very compact formulas for all the amplitudes. This for the double production and the single production. And in this case, I'm just showing for the dark matter case where we have spin 2. So now, as expected, your phenomenology, you're more restrict. So the parameter space is now has this constraint come from the decay and gamma rays. But still, you're allowed to have a reasonable window for your dark matter mass. We also study what is the regions where you have like this single production that are dominant in the most of the parameter space, and that this kind of double production, in fact, just take place for values outside of the EFT region. So I think this is what I wanted to say. So I hope that I could show to you that this kind of on-shell methods can be applied to study EFTs, that this unitarity, locality, and Lorentz symmetry are indeed powerful tools and allowed us to study high spin dark matter scenario. We didn't need to talk about Lagrangian, so this was kind of toy examples of how these methods can be applied also in the context of like model building. And I'd be happy to discuss more applications, and please just send me an email also if you want to discuss further or after the talk. Yeah, that's it. Thank you very much.
Thank you very much, Camila, for this clear talk. So I wanted to say that anyone can also write questions in the chat, also during the talks, in the next talks or after. But if there are any questions to Camila now, please. Rogerio.
So thank you, Camila, for the talk. I have one question. You know, I'm old guy, so I like Lagrangians. I know they're not perfect, but one thing that comes to mind is the following. So sometimes you have SUN symmetry. How the n goes into the amplitude? How do you find what n is? You don't have this information, right? If you're just writing amplitudes.
Yeah, I mean, the first thing that I want to say is that I'm not against Lagrangians. So I'm just like, you use whatever it's you have in hand and what can be easier for you to, you know, make the calculation. So this is true that for some things it's I mean, it's still not clear how to build things with directly with the amplitudes. In the case of the SUN, I think you have to, I mean, I didn't discuss, but you have to work out what is the color structure of the theory separated. So you normally write, you know, I don't know if you have a fundamental or adjoint, and then you see how you can decompose your full amplitudes in this, call it color order amplitudes. And I think this is where it's going to appear kind of the information, which group you're talking about. Yeah.
Okay. And the second question, not a question, just a curiosity about more applications. So it just came to my mind. I remember reading these papers of the cosmological collider papers of Massless and Arkani Hamed, where they try to see if there's an effect of higher spin particles in the early universe in inflationary phase. Are people using these amplitudes also for this scenario where they want to study the effects of higher spin particles in the scattering amplitudes in the early universe, and how can the signatures that comes out from this?
Actually, I think not that I am aware. So you see, the thing is that not many people of the amplitude community were interested in applications with like more BSM. So this is what we are trying to do now. So I'm not sure if there's something in this direction, but maybe it's something interesting. I'm not aware of the paper. Okay. Maybe we can talk later. Maybe we find something to do.
That would be great. Thank you, Camila.
Yeah. Nicolas?
Okay, thanks, Camila, for the super nice talk. So I got confused. If you could please go back to your slide. I think it was 32 when you have the Higgs portal. Mm-hmm. It seems that dark matter decays there, no? In your scenario.
Yeah, decays, but there is like we put a bound in the. This comes from the decay, basically. It's gonna cut.
But here you're saying that heavy dark matter is excluded because of that, right?
Yeah.
I would have expected the up. No. No. Okay, it's fine. Yes. Okay. Yes. Okay. But for instance, could you forbid this kind of couplings? I mean, having just a completely stable dark matter?
Yeah, I think like in principle, you can now play with the model. What we want to like kind of just show these two examples of how you can kind of build the EFT and put the assumptions that you want. But I think, yeah, you can build a way to forbid this coupling and then like say that, for example, if you want to allow just this self-coupling and see what is the effect, for example. Yeah. This also would be, yeah.
Thanks.
Are there further questions? Camila, do you have in mind some model where there is a natural dark matter candidate with spin 3 or 5.5 or 4?
I think there is some papers that work with some kind of composite scenarios where you have a large group in the UV, and this can give you some stable higher spin dark matter particles. So this would be like kind of an example of UV completion. But this would be something that would be also interesting to understand better. Like we made some very general assumptions of how For example, the Wilson coefficient scale. So it would be nicer to also understand better how this happened in different UV's completions for this type of models.
Okay. Are there more questions or comments? Okay, maybe well, thank you again, and we can continue with the talk.